Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine standing alone in the middle of a vast desert, horizons stretching endlessly in all directions, not a soul in sight. Now replace the sand with stars, billions of them, and stretch that desert to infinite proportions. That's our universe. But here's the catch. It's not just standing still, it's growing, not slowly, not steadily, but faster and faster, as if someone pushed a cosmic accelerator pedal. The galaxies, like distant lanterns scattered across this boundless landscape, aren't just drifting. They're sprinting away from each other at ever-increasing speeds. If this sounds like science fiction, think again. This is our reality. And behind this accelerating expansion lies the most profound mystery in modern physics: dark energy. In 1998, a discovery shook the very foundations of cosmology. Two competing teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, embarked on a mission to measure the rate at which the universe's expansion was slowing down. The logic seemed solid. Gravity, which pulls everything inward, should be working tirelessly to decelerate the momentum from the Big Bang. As they observed Type 1a supernovae, which serve as reliable cosmic mile markers due to their consistent intrinsic brightness, the teams expected to find signs of a universe gradually coasting to a halt. Instead, the supernovae were fainter than expected, farther away than they should be. This could only mean one thing: the universe wasn't slowing down, it was speeding up. Let's stop and unpack that. Type 1a supernovae occur when a white dwarf, what's left after a star like our Sun dies, steals matter from a companion star until it reaches a critical mass of about 1.4 solar masses. It then explodes in a thermonuclear blaze, visible across billions of light years. Because these explosions are so uniformly bright, they allow astronomers to calculate their distance using the inverse square law of light. The farther they are, the dimmer they appear. By combining that distance with redshift, the degree to which the light from these supernovae is stretched by the expansion of the universe, astronomers can construct a map of cosmic expansion across time. And that's what led to the stunning revelation. Instead of curving inward like a ball tossed into the sky, the expansion curve was bending outward. Some unknown force, was pushing the universe apart with ever-increasing strength. This force was dubbed dark energy, a name as mysterious as the phenomenon itself. According to current measurements, dark energy makes up roughly 70% of the entire energy content of the universe. To put that into perspective, imagine a cosmic pie chart. Ordinary matter, all the stars, planets, gas clouds, and life, accounts for just under 5%. Dark matter, the invisible glue holding galaxies together, takes about 25%. And the remaining 70%. That's dark energy. It doesn't shine, it doesn't clump, it doesn't emit or absorb light, but it dominates everything. So, what is it? One possible explanation lies in Einstein's famous equations of general relativity. In 1917, even before Hubble discovered the expanding universe, Einstein added a term to his equations called the cosmological constant, represented by the Greek letter lambda, to keep the universe static because he believed the cosmos was unchanging. After Hubble's findings in 1929 revealed that galaxies were receding from each other, Einstein discarded lambda, calling it his greatest blunder. But decades later, that same constant re-emerged as a potential candidate for dark energy. If space itself has an inherent energy density, even in the absence of matter and radiation, it could behave as a repulsive force, pushing the universe outward. However, there's a catch. When quantum physicists try to calculate the expected value of this vacuum energy using known particles and fields, they arrive at a number that's absurdly large, about 10 to the power of 120 times greater than what we observe. That's a 1 followed by 120 zeros. This discrepancy is so vast that it's often cited as the worst theoretical prediction in the history of science. It raises a disturbing question. Why is dark energy so small yet not zero? And why is its effect becoming dominant just now, when the universe is roughly 13.8 billion years old. This is known as the cosmic coincidence problem. If dark energy had become dominant too early, galaxies and stars wouldn't have had time to form. If it emerged too late, we wouldn't be seeing acceleration today. Why now? Why us? Alternative theories abound. Some propose that dark energy is not a constant, but a dynamic field, dubbed quintessence, that changes over time, much like the scalar fields that may have driven cosmic inflation shortly after the Big Bang. Others suggest we need to tweak gravity itself, extending Einstein's equations to include extra dimensions or modified interactions on cosmic scales. These ideas are being tested with incredible precision, using tools like baryon acoustic oscillations, gravitational lensing, and the detailed mapping of cosmic microwave background fluctuations by missions such as WMAP and the European Space Agency's Planck satellite. The discovery of the universe's accelerating expansion was so groundbreaking that it earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. But the journey is far from over. Dark energy remains a shadowy enigma, unseen, untouchable, yet utterly essential. It doesn't just affect galaxies billions of light-years away. It determines the future of the universe itself. Will expansion continue forever, cooling the cosmos into a silent, dark abyss? Will the force of dark energy grow stronger over time, leading to a big rip that tears apart galaxies, stars, planets, and even atomic particles? Or is it an illusion, a misinterpretation of data, hinting at a deeper, more exotic truth about the universe's structure? Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. The accelerating expansion of the universe isn't just a fascinating curiosity, it's a wake-up call. It tells us that the cosmos is far stranger, far more complex and far more alive with hidden forces than we ever imagined. This is the story of our universe in motion, and we've only just begun to chase it. To truly understand the magnitude of the universe's accelerating expansion, we need to step back to a time when the very idea of cosmic growth was revolutionary. Imagine the early 20th century. Albert Einstein had just published his theory of general relativity in 1915, redefining gravity not as a force but as the warping of space-time itself. In this new view, massive objects curve the fabric of the universe, and smaller objects follow those curves. Yet when Einstein applied his equations to the cosmos as a whole, he ran into a problem. According to his math, the universe should either expand or contract. It couldn't remain static. But at that time, no one had observed anything suggesting motion on such a massive scale. To fix this, Einstein introduced a term into his equations, the cosmological constant, or lambda, a kind of anti-gravity that counteracted gravity to keep the universe balanced and unchanging. Fast forward to 1929. At the Mount Wilson Observatory in California, Edwin Hubble was peering through what was then the world's most powerful telescope. He noticed something astonishing. Distant galaxies were not only receding from us, but the farther they were, the faster they seemed to be moving away. This observation became known as Hubble's law, and it shattered the idea of a static cosmos. The universe was expanding. Einstein's blunder, the cosmological constant, was suddenly not a mistake at all, but a glimpse of something deeper. Still, in those early days, cosmologists thought the expansion would slow over time like a car coasting uphill, eventually grinding to a halt or reversing into a collapse. The idea of an accelerating expansion wasn't even on the table until the late 20th century. Through the 1960s and 1970s, scientists sought to measure the deceleration parameter, literally, how much the universe's expansion was slowing down. But the tools were blunt and the data noisy. Enter the 1990s. A new generation of telescopes, detectors, and computational techniques made it possible to test cosmic acceleration with unprecedented precision. At the heart of this effort was a particular type of star, the Type 1 supernova. These cataclysmic explosions shine with nearly uniform brightness, making them ideal standard candles for calculating distances across the universe. Two global teams of scientists working independently began using these supernovae to chart the universe's expansion history. The Supernova Cosmology Project, based in the United States and led by Saul Perlmutter, and the High-Z Supernova Search Team, an international collaboration spearheaded by Brian Schmidt and Adam Rees, raced to gather and analyze data from these distant explosions. They used telescopes like the Keck Observatory in Hawaii and the Cerro Tololo Inter-American Observatory in Chile, scanning the skies for dying stars. As they compared redshifts to brightness, something strange emerged. The farthest supernovae were not where they were supposed to be. They were too dim. They appeared farther than expected for a universe slowing under the influence of gravity. It was as if the universe had been expanding faster in the past than any decelerating model could explain. But that didn't make sense, unless something was pushing everything apart. This was the moment of revelation. The teams cross-checked their data. They adjusted for dust, galaxy type, and selection bias. Still, the signal persisted. The only viable conclusion: the expansion of the universe wasn't decelerating. It was accelerating. This result was announced to the world in 1998, and it landed like a thunderclap. The implications were staggering. It wasn't just that the universe was expanding. It was being driven by some unknown force that worked against gravity itself. A force that didn't clump or collapse, but instead infused empty space with energy. The term dark energy was coined not because we understood it, but because we didn't. It was invisible, unmeasurable through traditional means, and yet its fingerprints were all over the cosmos. Let's pause and appreciate the historical irony. Einstein had introduced a cosmological constant to keep the universe static, only to discard it after Hubble's discovery. Now, 70 years later, scientists were putting it back into Einstein's equations, not to keep the universe in balance, but to explain why it was speeding up. And here's the twist. The modern cosmological constant is not quite the same as Einstein's original concept. In today's models, lambda represents vacuum energy, a kind of energy that remains constant as the universe expands. Unlike radiation or matter, which dilute over time, vacuum energy's density stays the same. So as space grows, there's more of it, meaning more dark energy. It's a feedback loop that drives faster and faster expansion. But how do we know this isn't just a fluke or a misreading of data? That's where the cosmic microwave background comes in. This ancient light, left over from just 380,000 years after the Big Bang, is a treasure trove of information. Satellites, like WMAP and Planck, have mapped tiny fluctuations in this background radiation across the entire sky. When combined with supernova data and large-scale galaxy surveys, these observations converge on the same startling conclusion. Our universe is flat in geometry, but dominated by dark energy in content. And then there's baryon acoustic oscillations, ripples, frozen into the distribution of galaxies, like sound waves imprinted across the sky. These cosmic ripples allow scientists to measure how the universe has expanded over time, serving as a kind of standard ruler. The results, once again, reinforce the picture, a cosmos accelerating under the influence of dark energy. It's a pure convergence of multiple lines of evidence, all pointing in the same direction. The discovery of dark energy wasn't just a turning point for astronomy, it was a philosophical earthquake. It forced scientists to reimagine the fate of the universe. If this mysterious energy continues to dominate, galaxies will drift farther and farther apart. Stars will burn out. New ones will cease to form. The cosmos will grow darker, colder, and more isolated. This is the heat-death scenario, also known as the Big Freeze. But some models suggest something even more extreme. If dark energy's strength increases over time, it could eventually overcome all forces, ripping galaxies, stars, planets, and even atoms apart. This apocalyptic idea is known as the Big Rip. 4. Now we live in a delicate balance. We don't know if dark energy is constant or evolving, if it's a property of space or a hint of some deeper dimension. We only know it's real. And it's here to stay. The accelerating expansion of the universe wasn't discovered with a single flash of insight. It was built on decades of patient observation, daring theory, and relentless curiosity. From Einstein's chalkboard in 1917 to supernovae exploding billions of light-years away, this is a story woven through time and space. If dark energy is the force accelerating the expansion of the universe, then the next logical question is, what exactly is it? This is where the mystery deepens, because despite measuring its effects with astonishing precision, we still don't truly know what dark energy is. In fact, calling it dark energy is a bit of a placeholder, a label, born from our ignorance rather than understanding. So let's venture into the domain where theory meets imagination, where the boundary between physics and philosophy blurs. Because when it comes to dark energy, science is still reaching in the dark. Let's start with the simplest and most widely accepted explanation, the cosmological constant. In this model, dark energy is the energy of empty space itself. Sounds paradoxical, right? How can nothing have energy? Yet quantum field theory, the bedrock of modern particle physics, tells us that even in a perfect vacuum, particles are constantly flickering in and out of existence due to quantum fluctuations. This isn't just science fiction. It's experimentally confirmed. These fluctuations create a baseline energy that permeates all of space, often referred to as vacuum energy. But here's where it gets weird. When physicists try to calculate the vacuum energy using quantum mechanics, the numbers they get are insane. According to the math, the energy density of empty space should be around 10 to the power of 120 times greater than what we observe from the acceleration of the universe. That's a 1 followed by 120 zeros. This is not a rounding error, it is the single biggest mismatch between theory and observation in the history of science. It's called the cosmological constant problem, and it's a screaming clue that something fundamental is missing from our understanding. So, if vacuum energy as we currently calculate it doesn't match observations, what are the other possibilities? One intriguing alternative is something called quintessence. Unlike the cosmological constant, which is constant in time and space, quintessence imagines dark energy as a dynamic field, one that evolves over cosmic time. Think of it like a ghostly mist filling the universe, slowly shifting and flowing, according to its own rules. Unlike matter or radiation, quintessence doesn't clump. It's smooth, diffuse, and interacts only through gravity. If true, it means that the acceleration of the universe could change in the future. It might slow down, speed up, or even reverse. This idea opens up fascinating doors. If dark energy is not a constant, then the fate of the universe could be far more complex than a simple freeze or rip. Some models suggest periods of acceleration followed by contraction, cosmic cycles of death and rebirth. Others imply that the universe might eventually stabilize into a new kind of equilibrium we can't yet imagine. But quintessence is just the tip of the iceberg. Other theories propose even more exotic mechanisms. One such concept involves phantom energy, a form of dark energy with even more negative pressure than the cosmological constant. Phantom energy would cause the expansion of the universe to accelerate so violently that it tears apart not just galaxies and stars, but atoms themselves. The fabric of space-time would be shredded. This is the ultimate version of the Big Rip, a final disintegration of all structure. Then there's the idea that dark energy might not be energy at all, but a sign that our understanding of gravity is incomplete. Think about it. General relativity has passed every test in our solar system with flying colors, but the scales involved in cosmic acceleration are unimaginably vast. What if gravity behaves differently on those scales? Modified gravity theories, such as FR gravity, scalar tensor theories, or brane world models, attempt to tweak Einstein's equations just enough to produce acceleration without invoking an extra energy component. Some of these models predict observable differences in how galaxies form and cluster, differences that next-generation surveys are designed to detect. One particularly mind-bending proposal involves extra dimensions. In theories inspired by string, Theory: our visible universe might be a three-dimensional brain floating in a higher dimensional space. Gravity, in this scenario, could leak into extra dimensions, becoming weaker on cosmic scales and mimicking the effect of dark energy. These models are beautiful, strange, and difficult to test, but not impossible. Then there's the anthropic principle, a controversial but unavoidable philosophical idea. In the multiverse hypothesis, a possible consequence of inflationary cosmology, there could be an infinite number of universes with different values of dark energy. Most of these universes would be either too chaotic or too empty for life to exist. But in the rare pockets where dark energy is just right, neither too strong nor too weak, structures like galaxies can form, stars can shine, and observers like us can ask these questions. It's a cosmic version of the Goldilocks principle. We're here because this universe happens to be suitable for life. This doesn't explain why dark energy has the value it does. It just argues that it had to be something like this in any universe where sentient beings could exist to wonder about it. Of course, some physicists find this deeply unsatisfying. They want a testable theory, a concrete mechanism, not an appeal to probability, and that's where the frontier lies today. Observatories like the European Space Agency's Euclid telescope and NASA's Nancy Grace Roman Space Telescope, scheduled for launch soon, are designed to measure the acceleration of the universe with unprecedented precision. By mapping billions of galaxies, tracking the large-scale structure of the cosmos, and refining our measurements of supernovae and baryon acoustic oscillations, these missions aim to pin down the properties of dark energy. Are they constant or variable? Is the acceleration smooth or bumpy? These are the kinds of questions we hope to answer within the next decade. We're also exploring the nature of dark energy through experiments on Earth. Though we can't recreate dark energy in a lab, we can test the laws of gravity with extreme precision, using atom interferometry, torsion balances, and gravitational wave detectors. Any hint that general relativity breaks down at certain scales could point the way to new physics, and perhaps a true understanding of this enigmatic force. So here we are, suspended in a universe we barely understand, driven apart by a force we can't see or touch, and yet we are chasing it across billions of light years through equations scribbled on chalkboards and into the very heart of what reality might be. Dark energy is no longer just a mystery, it is a compass, a trail that, if followed, could lead us to the next great revolution in physics, one that unites the quantum and the cosmic. We've explored the dark energy driving the accelerating expansion of the universe, but we've only scratched the surface of the real story, the cosmic consequences of this mysterious force. What happens to the universe as it continues to accelerate? Will it simply expand forever, growing colder and more isolated? Or could the universe be headed toward an even more extreme fate, one that will shatter everything we know? To understand where the universe is headed, we need to dive into the potential fates that await it in the far future. Let's start with the most likely scenario, the Big Freeze. In this scenario, dark energy continues to push galaxies further apart at an accelerating rate. The universe will keep expanding, and stars will gradually run out of fuel. The first to go will be the smaller, less massive stars, red dwarfs. They will burn through their fuel over billions of years, gradually fading into the void as they reach the end of their lifespans. As the stars dim and fade, new stars will become increasingly rare. The gas that fuels star formation will slowly be consumed, leaving behind a dark, starless cosmos. Meanwhile, the galaxies will drift further apart. The vastness of space will increase dramatically, and even the nearest galaxies will become distant, unreachable islands. The Andromeda Galaxy, our closest large neighbor, is currently on a collision course with the Milky Way. It's expected to merge with our galaxy in about 4 billion years. However, under the influence of dark energy, that collision may not even happen. The accelerating expansion could push galaxies beyond each other's reach before they ever collide. Instead of a grand merger of galaxies, we could witness the slow dissolution of galactic clusters, leaving them isolated in the expanding void of space. The ultimate fate of this Big Freeze is a universe that becomes increasingly empty and dark. The last stars will burn out, leaving behind cold, dark remnants, white dwarfs, neutron stars, and black holes. These stellar corpses will persist for countless billions of years, but eventually, they too will fade away. Neutron stars will slowly lose energy through a process called gravitational radiation, and black holes will lose mass through a phenomenon known as Hawking radiation, a slow evaporation predicted by physicist Stephen Hawking. But even that process will take unfathomable lengths of time, far longer than the current age of the universe. After all the stars have burned out, the universe will be a dark, cold expanse, with black holes scattered throughout. The temperature of the universe will approach absolute zero as the final vestiges of heat disperse. In the farthest reaches, even black holes will evaporate, leaving only the faint traces of radiation in an otherwise empty and desolate cosmos. This would be the end of time as we know it, the ultimate conclusion to an ever-expanding universe. But what if dark energy behaves differently? What if its strength doesn't remain constant, but instead increases as the universe continues to expand? This would lead to an even more dramatic fate, the Big Rip. In this scenario, the force of dark energy grows stronger over time, tearing apart galaxies, stars, planets, and even atoms. The first to be affected would be galaxies. As the acceleration of the universe increases, the gravitational pull between galaxies will weaken, causing them to pull further and further apart. This would be the end of galactic clusters and the cosmic web, structures that hold galaxies together. Each galaxy would become isolated, drifting farther from others. Next, the expansion would begin to tear apart individual stars. The force of dark energy would stretch the stars apart, ripping them from the inside out. Over time, even the planets and moons orbiting these stars would be flung away into the ever-expanding universe. The Earth, for instance, would be torn apart long before this final fate, but even the distant remnants of solar systems will eventually be scattered to the winds. At its most extreme, the Big Rip would continue to escalate. The next step would involve the destruction of atoms. As the fabric of space-time stretches even more, the fundamental forces that hold atoms together would be overcome by the expanding force of dark energy. The very structure of matter, protons, neutrons, and electrons, would be torn apart. Everything from the largest galaxies to the smallest subatomic particles would be shredded. This is the most extreme apocalyptic vision of the universe's future. But there's a reason it's considered by some to be an unlikely scenario. The rate at which dark energy's strength would need to increase to cause the Big Rip is far beyond what current observations suggest. So while the possibility exists, it is still a matter of great debate. Most scientists think the Big Freeze remains the most plausible fate, an eventual decline into cosmic emptiness, where the universe becomes a vast and desolate landscape. Then, there are the theories that entertain a more optimistic future. Some researchers argue that dark energy may not be a permanent force, or that it could one day evolve into something else entirely. One idea involves the possibility of a cosmic bounce, a cyclical universe in which the Big Bang was not the beginning, but one of many cycles of expansion and contraction. In this model, after the universe reaches its maximum expansion, the effect of dark energy could reverse and gravity could take over. The universe would collapse inward, potentially leading to another Big Bang. This cyclical view of the universe implies an infinite loop of creation and destruction, where the fate of the universe is not final, but eternal. Other models suggest that dark energy could eventually become unstable, triggering some form of catastrophic event. Perhaps dark energy will evolve into something even more exotic, resulting in a cosmic phase transition where the laws of physics as we know them change. Some physicists speculate that such a transition could radically alter the behavior of the universe, transforming it into a completely new phase, one with entirely new physical laws. As we explore these potential outcomes, the future of the universe remains deeply tied to our understanding of dark energy. What we discover in the next few decades, from new surveys of distant supernovae to advanced probes of the cosmic microwave background, could dramatically reshape our vision of the cosmos. The universe is not static, and its ultimate fate is not written in stone. We are part of an ongoing cosmic drama where new chapters unfold as we uncover deeper truths about the fabric of reality. But there's one thing we can be certain of: the universe is far from boring. Every new discovery opens up more questions, more mysteries to unravel. And perhaps in a distant future, we will have answers to these questions, answers that could reshape our understanding of existence itself. We've traversed through the cosmic void, unveiling the enigmatic force of dark energy and exploring its role in the accelerating expansion of the universe. But as we stand at the edge of what we know, we're faced with a compelling question. What is the true significance of dark energy in our quest to understand the universe? Is it merely an oddity of physics, or is it the key to unlocking a far deeper, more profound mystery, one that might reveal not just the fate of the universe, but its very origins? One of the most exciting aspects of our exploration of dark energy is the realization that it challenges everything we thought we knew about the cosmos. For centuries, scientists believed that gravity would eventually slow down the expansion of the universe, pulling everything back together. We imagined that the fate of the universe would be determined by the balance between the initial push of the Big Bang and the gravitational pull of all the matter in the universe. But instead, dark energy has defied this expectation, proving that the cosmos is far more complex than we could have ever imagined. The expansion isn't slowing, it's speeding up, and if this acceleration continues, it could change the entire trajectory of cosmic evolution. What's even more captivating is the possibility that dark energy could offer us a glimpse into the deepest workings of the universe. Could it be tied to the very fabric of space-time itself, a force that is built into the architecture of the cosmos? Some theories suggest that dark energy could be linked to the so-called vacuum energy of empty space. This could point toward a deeper connection between the fundamental forces of nature. The true nature of dark energy could ultimately provide the missing link between general relativity, which governs the large-scale structure of the universe, and quantum mechanics, which rules the microscopic realm. Perhaps dark energy is not an independent force at all, but rather a consequence of some unknown quantum field or interaction. This idea has led to some mind-bending proposals. What if dark energy is a manifestation of an underlying dark sector of the universe, an unseen counterpart to the familiar matter and radiation we observe? Some speculative theories even suggest that dark matter and dark energy are part of the same mysterious entity, two sides of the same cosmic coin. If true, this could completely reshape our understanding of what the universe is made of. Yet despite all the tantalizing ideas and cutting-edge research, we still have little more than theories to go on. The question remains, what is dark energy, really, and what role does it play in the cosmos? For now, the answer continues to elude us, slipping through our fingers like the elusive threads of the universe itself. But this very uncertainty is part of the beauty of science. Each new discovery, each new observation, brings us one step closer to unraveling the most profound mystery of all, understanding the nature of the cosmos and our place within it. We live in a time where every day scientists across the globe are uncovering new clues, testing new theories and pushing the boundaries of human knowledge. The fact that we are even able to ask these questions is a testament to the incredible progress we've made. We've sent spacecraft beyond the outer reaches of our solar system, detected the faintest ripples in space-time, and witnessed the birth and death of stars. Yet, as we gaze into the vastness of the universe, we realize that we've only begun to scratch the surface of what's out there. What will the next generation of explorers discover about dark energy? Will we uncover the fundamental mechanisms behind its mysterious influence? And if we do, what other secrets of the universe will it reveal? Perhaps dark energy is just one piece of a much larger cosmic puzzle, one that, when solved, could transform our entire understanding of the universe and everything within it. Imagine if the discovery of dark energy is merely the first step on a journey toward discovering the deeper truths of the cosmos, truths that could change how we think about space, time, and even reality itself. The universe is vast, and its mysteries are infinite. And while dark energy remains one of the most confounding, it is also one of the most exhilarating. Each new piece of information we uncover brings us closer to understanding the true nature of the universe, a journey that will continue for generations to come. But we don't have to wait for future scientists to discover these answers. We're part of this grand journey too, aren't we? Every time we ask questions, every time we ponder the unknown, we're contributing to the ongoing exploration of the cosmos. The mysteries we uncover today may lay the groundwork for the discoveries of tomorrow. As we close this chapter in our understanding, remember this: the universe is full of secrets. Dark energy is just one of them. And the more we learn, the more we realize just how much there is left to discover. So as we stand at the edge of the known with only the faintest glimmer of understanding, let's keep pushing the boundaries. Let's keep asking questions, seeking answers, and venturing boldly into the unknown. If you've enjoyed this exploration of the universe's biggest secret, dark energy, there's so much more to uncover. Like, share, and subscribe to Cosmics Whispers for more cosmic mysteries, and join the journey as we continue to unlock the secrets of the universe. And as always, we'd love to hear your thoughts. What do you think dark energy could be, and where do you see the universe headed? Drop your thoughts in the comments below. Until next time, keep looking up, because the universe is waiting to be discovered.